Hello, my name is Emma Brooks, and I'm a senior majoring in math and computer science and minoring in data science. And I'm excited to talk to you today about my project on examining women's health equity with machine learning techniques. My research objective for this project is to predict the time between diagnosis and first treatment appointments for triple-negative breast cancer patients. And my main research included learning about predictor selection processes and finding flexible and accurate machine learning models in R. I obtained my data through Verity Health from the Women in Data Science Datathon, and each observation or row in the data set is a triple-negative breast cancer patient, and there's a total of 27,674 patients. My response variable, also called the independent variable, is the days between diagnosis and first treatment appointment, and this is also called the treatment period. And I have a total of 83 predictor variables, which can also be known as dependent or explanatory variables. And these are a blend of patient characteristics such as age and diagnosis year, and patient location characteristics such as median income for the zip code area, and the proportion of white residents for a zip code area. So predictive modeling and machine learning. The goals of predictive modeling is to estimate a function that can be used to predict a response. And we have inputs into this function that are our predictor and explanatory variables. In this project, the response is the treatment days we're trying to predict, and our predictor variables are the patient characteristics. And there are many ways to do predictive modeling, such as linear regression, where we have a function that we can write down, but there are also ways such as random forest where we cannot write down this function. And I will be using both of those techniques. And machine learning can help us achieve the goals of predictive modeling. Machine learning is an area of artificial intelligence that uses existing observations to train a model and make predictions on unseen data. So we have existing patient data already that we are training our model with, but we are hoping that our model can perform well against new patient data. So the machine learning models I'll be focusing on are linear regression and random forests. And we have to talk about decision trees in order to understand random forests. So linear regression, we are modeling the relationship between a predictor and a response variable as a linear equation. And in order to make the predictions, we would just plug in values for those predictor variables, and it would output our prediction. And a decision tree, we are essentially dividing the predictor space into smaller and simpler regions by a set of rules, and these rules form a structure of an upside down tree. We can think of a decision tree as a flow chart where you have to make a decision at each point in the tree, and that will eventually lead to your endpoint. So in the image here, we're trying to predict what animal based on the characteristics of the animal. So maybe we have a penguin and we go down the flow chart. Does it have feathers? True. Can it fly? False. So our tree predicted that our animal is a penguin. And a random forest is a collection of these decision trees where each tree is fit with a random sample of our training data. And at each point in these individual trees, there's a different set of predictor variables that are considered to be the criteria or the rule at that specific point in the tree. And in order to get our final prediction from the random forest, we are averaging each of the individual predictions of the trees. So to prepare my data, I split my data into a training data set and a testing data set. And we do this because we are fitting our model with the training data set, and we are assessing the accuracy of our model with the testing data set. So the testing data set is essentially serving as our unseen data. I also deleted variables with too many missing values, and I added variables such as metastatic cancer body system, which denotes the area of the body the cancer has spread to, and breast cancer diagnosis side, which denotes which breast was diagnosed with cancer. I also eliminated variables that were highly correlated, and I Windsorized the response variable, which I'll talk about more in the next slide. I also did a natural log transformation to the response, but only for the linear model. And I made an R function to make all of these changes to the testing and the training data. So here's a look at our response variable, the treatment period, and on the left, here's the unchanged version and the unchanged distributions, and we can see that it is very right skewed and very affected by outliers. So the Windsorizing will help us with that extreme skewedness. And Windsorizing is essentially replacing outlier values with less extreme values. And for this transformation, I will be replacing all values above the 80th percentile with the value of the 80th percentile. So we can see after the Windsorization, our distribution is looking a lot more normal. And we can see here on the right in the histogram, that very tall bar, those are all of the outliers that were replaced with the 80th percentile value. We can also see that our maximum value is now what the former 80th percentile was. Next, I wanted to look at variables that had possible relationships with our response variable, and this is helpful because we can see which predictors might be useful in our model. I first checked the metastatic cancer body system to see if there were any differing box plots with the treatment period, and there were. We can see that for example, the lymphatic body system interquartile range is much different than the nervous system interquartile range, as well as the median. So these differing box plots can indicate that the metastatic cancer body system variable could have a relationship with our treatment period and could be useful in our model. Next, I wanted to see if the treatment period was varying by the year the patient was diagnosed. We can see that in 2015, it's looking much different than 2016, 2017, 2018. We're seeing that the distribution of the patients here, they tended to have to wait a little bit longer if they were diagnosed in 2015. And this was concerning. So I wanted to see if patients diagnosed in 2015 had any other differences. Next, I was looking at the cases diagnosed by year, and I colored by which breast was diagnosed. And we can see here that 2015 is also very different from the other years, where a high proportion of the cases were diagnosed with an unspecified breast. Next, I wanted to check the metastatic cancer body system to see if that differed by years as well. And we can see that 2015 differs a little bit with a little bit more skeletal cases than the other years, but for the most part, most of these cases are lymphatic. And I will be measuring the accuracy of my machine learning model with the root mean square error, and I'll be using this with the testing data. And the root mean square error is essentially the average difference between the predicted and observed values. And on the left image here, we can see that the difference between the predicted and the actual value is the error, and we are essentially trying to measure those up throughout the whole model. And on the right here, we have our formula for the root mean square error, where we have the predicted values that our model put out and the observed values that are already existing in our testing set, and we subtract that and square that difference in order to keep a positive value to get the distance, since errors can be negative. And the summation and divided by n, that's part of calculating the average. And then we square root in order to undo our previous square and get back to units we're familiar with. And finally, here are my model results. So for my linear regression, I got a root mean square error of about 173 days. And this can be interpreted as, on average, our predictions were about 173 days off from observed values. And I had a natural log transformation for this linear regression, but I originally started with 20 predictors for the linear regression, but I used backwards selection in order to get the best version of this model, and ended up with 8 predictors. And next, onto our random forest. As you see here, I have 2 extra columns for the random forest table, but mtry and number of trees. And mtry is essentially the number of variables that are considered at each point in the tree. And then the number of trees, those are the number of trees in the forest. So without the Windsorization transformation, our root mean square error was about 161 days, which wasn't great, but we can see with the Windsorization, it helped a lot, and our model performed much better without all of those outliers. So our random forest definitely performed better than our linear regression, and I was expecting that result. So our very important predictors, these were some of the most important predictors for our predictions. We have breast cancer diagnosis year, which we looked at, breast cancer diagnosis side, which we also looked at, patient age, metastatic cancer body system, which we looked at, and rent burden. And rent burden is a characteristic of the zip code location, and it is the median rent as a percentage of the median renter's household income. So these are very important factors to look into for patients. So in conclusion, our random forest was the most accurate model, as I was expecting, and the Windsorization helped even more. So for future research, I would want to try other machine learning models, or possibly more hyperparameters that I could try to tack on along with the M-try and the number of trees. And in context of the original problem, I think our very important predictor findings could indicate characteristics that are affecting patients from getting good early care. And then I would also like to research the changes between 2015 and other years to see what changed between 2015 and 2016 that was causing patients not to get a quicker treatment period. Like, were there policy changes or were there any discoveries in the field that led to better care? So that is all. Thank you so much.